So chapter 3.2, the concept that we're looking at is there are 4 emergent properties of water, and these contribute to Earth's suitability for life. So like we said in the last section, Earth is very suitable for people and all life to happen here, and it's because of water. And there's 4 reasons. The emergent properties, think back to last chapter about what emergent properties are, and these are that cohesive behavior, the ability to moderate temperature, expansion upon freezing, and versatility as a solvent. And we'll see that these 4 things are why we can live with water. So first is cohesion. So water molecules stay really close to each other because of hydrogen bonds, which we talked about in the last section. And they're linked together by many, many hydrogen bonds. So the water molecules are always next to each other. And water as a substance tends to stick together, and that is because of these hydrogen bonds. And water molecules sticking to other water molecules is a phenomenon called cohesion. So this is what we're talking about. Cohesion of water molecules is one water molecule sticking to another water molecule. Cohesion. And cohesion helps the transport of water against gravity in plants. So obviously the top of a plant needs water as much as the bottom of a plant does. And water in plants comes from roots. So we need water to stick to each other, and it helps pull up water from the roots. That's cohesion. Adhesion is when water molecules stick to something else. It's different, not another water molecule. And this also fights against gravity, so water also climbs up inside of a plant. We'll talk a lot about cohesion and adhesion more when we come to plants, but you have to understand that water sticks to itself and it sticks to other things. And this is why plants can live, because if we couldn't get water up to the top against gravity, we wouldn't have any plants that grew out of the ground. They would all be like moss and stay on the ground. So inside of a plant, we have these things called xylem, which water moves through. We'll get there much later, but you need to know that because of cohesion and adhesion, that's why we can have plants. Basically, because these leaves up here would never be able to get any water because the water all comes from down here. It needs to move upward. So water sticks to itself right here, cohesion, and it sticks to the inside of these vessels called adhesion. And so it climbs and pulls the other ones up behind it. So that's how water gets to the top of a plant. Cohesion also leads to something called surface tension. And surface tension, by definition, is a measure of how hard it is to break the surface of a liquid. And it's very closely related to cohesion, and it's because water molecules are all sticking to each other, right? So they're sticking more to each other than to air, because air isn't really a surface. So at the top of a body of water, there's water underneath and an air above. And so all of the water molecules are sticking to each other through the hydrogen bonds, and they are not sticking to the air, obviously. And so it kind of forms this barrier. This makes the water behave as though coated with an invisible film, so your textbook says. And because of this, you can kind of see if you fill up a glass of water, you can fill it up a little bit taller than it is because that's surface tension, and all the water molecules are sticking to each other. And this allows for crazy things like this, where different very lightweight bugs can walk on water. The next property that we're going to talk about is moderation of temperature by water. So basically, water absorbs heat from warmer air and releases stored heat to cooler air. So you have a glass of water and it's warm outside. The air is warmer than the water. Water is going to absorb the heat. If it's cooler, then water is going to release the heat. And it can absorb a lot of heat without really changing temperature. So first let's talk about what some of these words mean. That way you can know the difference between heat and temperature. So first and foremost, anything that moves has kinetic energy. That is the energy of motion. If you're moving, the energy that is doing the movement is called kinetic energy. And atoms and molecules always have kinetic energy. They're always moving. They're never still. And the faster you move, the greater kinetic energy you have. And heat is a form of energy, and it measures the total amount of kinetic energy from molecular motion. So heat is a measure of kinetic energy. So how much actually is there? And volume is a factor. So if you have a glass of water, it's this big, versus a gallon of water, there's going to be more heat in the gallon of water, generally, because there's more water. There's more energy happening in there. This is different than temperature, because it's not the same thing. Heat and temperature are not the same thing. Temperature measures the average kinetic energy of molecules. So volume is not a factor when it comes to temperature, because it's the average. So if you're making coffee, for example, you're adding heat to it. And so the molecules start to move a whole lot faster. The thermometer measures a higher temperature, because overall there's more kinetic energy on average in the coffee, in the hot water after you heated it then beforehand. Whereas if you're going to compare a swimming pool to a pot of coffee, so the swimming pool in my backyard, it's pretty cold right now, haven't heated it, whereas the coffee pot over there with some hot water in it is much hotter. However, there's much more heat in the swimming pool, because it's the total amount of kinetic energy versus the average amount. So the coffee has a higher temperature, but the swimming pool has has more heat. So that's the difference between heat and temperature. And the way that we measure these is in science, we always use Celsius. And Celsius is a measure of temperature using Celsius degrees. So again, we're measuring the average with Celsius. And a calorie is the amount of heat, so remember how much kinetic energy there is in total, required to raise the temperature of 1 gram of water by 1 degree Celsius. So let's say we have 1 gram of water. How much heat, how much molecular motion is there going to need to be so that that gram of water goes from 12 degrees Celsius to 13 degrees Celsius? That's what a calorie is. And the calories on food packages are actually kilocalories, kcal, where 1 kcal equals 1,000 calories. So a calorie is a measure of heat, a measure of energy. So in terms of food, it's how much energy do you need to metabolize what you're eating. Another unit of energy that we use is called the joule, not J-E-W-E-L, but J-O-U-L-E, and it's just another unit of energy that you will sometimes hear about. So basically heat is always going to move, it's always dispersing. So heat is always going to move from whatever's warmer to whatever's cooler. And so if you have, like in this glass of water, there's, this water was room temperature when it was poured, and then the ice was frozen, obviously. So the ice is cooling down the water, not because it's giving coolness to the water. What it is, it's taking heat out of the water. And so as it takes heat out of the water becomes cooler. So that's how ice works. And as the ice absorbs the heat, it melts, because now it's warmer. And as water gets warmer, it melts, obviously. So water has something called, has a very high specific heat. And this is another vocabulary word you need to know. The specific heat of a substance is the amount of heat, so how much molecular motion, that must be absorbed or lost for 1 gram of that substance to change its temperature by 1 degree Celsius. So it's similar to calories again. The specific heat of water is 1 calorie per gram per degree Celsius. And the specific heat of water is unusually high. So water does not change temperature very easily because it has such a super high specific heat. So the specific heat of water, like I said, is 1 kcal per gram per degree Celsius, whereas with rubbing alcohol, it's 0.6 cal per gram per degree Celsius. So almost half the amount of heat is required to change a gram of alcohol by 1 degree Celsius as it is to water. So much higher with water. And the reason for this is because of the hydrogen bonds. That's why. Again, we're always going to come back to hydrogen bonds. So like I said, water's temperature is very difficult to change. So think of it this way. You're boiling water, and you're trying to boil water, and the water inside isn't boiling yet. It's just kind of lukewarm. But the iron pan that you're boiling it in, you touched it, you would probably burn your hand. Now, how does that make any sense? The water inside is lukewarm, but the iron pan outside is burning hot. It's because iron has a much lower specific heat than water. So you need much less heat to make the iron feel hotter than the water. It's kind of a confusing concept, but we'll talk about it a lot. So basically, specific heat is a measure of how much a substance is going to resist changing temperature. And like I said, water's high specific heat is from its hydrogen bonding. So heat is absorbed when hydrogen bonds break, and heat is released when hydrogen bonds form. So as water absorbs heat, the heat goes into the hydrogen bonds and kind of breaks them. The heat is making the molecules move more, so as they're moving, we're breaking the hydrogen bonds. And as water loses heat, the hydrogen bonds start forming, the water molecules are moving more slowly, and so the heat is leaving, and we're making new hydrogen bonds. And the reason that this is so important is because the high specific heat of water keeps water relatively from changing temperature easily, and it allows for life. Because think of it this way, if the if the ocean was changing temperature super easily based on the time of day because of the sunlight or the heat coming from the sunlight, we wouldn't be able to have life the way that we do. So think of it this way. So it regulates, the high specific heat of water regulates not only like ocean temperatures, but temperatures on land. So we're really lucky that we live relatively close to the water, because this giant body of water takes in a lot of heat and releases a lot of heat, and keeps the areas over here cool. That's why if you ever have to drive inland, it's so much hotter because the water isn't there controlling the amount of heat in the air. So that's really important. Then the next important thing about temperature and water is evaporation. So as water molecules absorb heat, they move fast enough and they break their hydrogen bonds. Now they're not sticking to each other as much. They're moving faster. Suddenly they're a gas. They're not a liquid anymore. And this is what we call evaporation, is a change of water from liquid to gas, or any substance from liquid to gas. And the heat of vaporization is the amount of heat that a liquid must absorb for 1 gram to be converted to a gas. So it's kind of like specific heat, except instead of raising by 1 degree Celsius, now we're changing from a liquid to a gas. And water has a very, very high heat of vaporization. As a liquid evaporates, its remaining surface cools, called evaporative cooling. So basically the hottest molecules are moving really fast and they're becoming a gas. So the hottest molecules are leaving behind the coolest molecules. So now what it left behind is much cooler. This is why we sweat if we are hot, because as we sweat, the heat is leaving our body in the form of the water. And so it's cooling down our bodies, and that's how evaporation and sweating work. Like I said, evaporative cooling of water helps stabilize temperatures in organisms and bodies of water. This really helps moderate the Earth's climate because solar heat is absorbed by bodies of water. And then the bodies of water don't change temperature very easily because of this really high specific heat of water. So this allows for a couple of things. One, living things can live much, much, much more easily inside oceans and bodies of water because the temperature isn't fluctuating like crazy. If the specific heat of water were lower, temperature would be all over the place, but it stays pretty constant, and it regulates the climate on land. That way we can live here more easily. If the temperature on land fluctuated with the heat coming from the sun, it would be 200 degrees during the day and negative degrees at night. So it's really important that the water, based on the high specific heat and the evaporative cooling, maintains the climate that we can live at. And the very last part is the insulation of ice. So as water freezes, it freezes from the top down. So that way things can keep living underneath, and it kind of insulates the body of water beneath. If things froze from the bottom up, there would be no life basically, because nothing could live in the oceans, and the oceans would never thaw, or the bodies of water would never thaw in the winter because only the top would get heated up. So basically the fact that water freezes on top really allows for life to live in bodies of water.